Okay, so we got the first of two presentations by Luke on the insulation part of the system, and we're going to start out with weathering in the carbon cycle.
All right, drink up your coffee, you know, that time of day, right? So let me see. What I want to do is I'm going to talk a little bit about weathering and its coupling to the carbon cycle, and eventually its coupling to some of the possible couplings to some of the large-scale issues that a lot of people in this room worry about. And weathering is a complicated, it's a complex phenomenon, and we have to worry about it at both sort of macroscopic and microscopic scales. And so I'll just frame it by saying, well, geez, this is what we start out with. This is pretty fresh rock right there. And actually, that's already beginning to alter, right? That's already beginning to change its composition. And you can hear it. You hear it like Rice Krispies going snap, crackle, and pop as the glass crystallizes the surface and pops off. And there are acid vapors that are already beginning to alter the composition of that basalt before it's even cold enough to touch. And then after a little while, depending on where you are, this is what you get, right? This looks pretty messy, and this is a soil profile from about a 350,000-year-old basalt flow on the north end of the Big Island of Hawaii. It looked just like that did 350,000 years ago. There are a few reasons why I like to work in Hawaii, and some of them are obvious. But one of them is we can actually sample everything from this morning's lava flow like you just saw, to stuff that's about 4 million years old, under a wide range of climate conditions, either very wet or in this case quite dry, and a wide range of ages. So it's pretty cool. So this is a soil, and soils are complicated, and I have often rued the day I ever got involved in doing soil geochemistry, because before that I was a nice geochemist, wore a white shirt, and dressed my pants and all that kind of stuff. And then I got involved in soil. It was sort of a slippery slope, and my alcohol consumption went up and all that kind of stuff, because they were just really one of the most complicated materials on the earth, and so nothing's at equilibrium, or not enough things are at equilibrium. It's a very, very open system. Here we've got the upper part. We've got amorphous iron oxides giving it the red color. So these non-crystalline aluminum silica mineraloids, which haven't crystallized yet. Some modern organic matter. Some rocks that are floated up by wetting drying events. Here's a clay that's mostly gibbsite and aluminum hydroxide. Here we've got pedogenic carbonate, which contains both components from the basalt and components from precipitation in the atmosphere. And you can imagine the hydrology of the system is complex too. And of course, water matters when you're doing weathering. So it's a pretty complicated animal. And I just want to kind of run down some of the things that we got to think about from both a microscopic and macroscopic scale. So to a first approximation, weathering is an acid-base reaction. And there's also oxidation reactions that go on if you have iron present and a couple of other things. But acid-base reactions are the way to think about it. And the most common source of acidity is carbonic acid, which is formed by the hydration of CO2. That carbonic acid is a weak acid. It will generate one proton, and bicarbonate ion in the second reaction there. It'll generate a second proton if the pH is low enough. If the pH is right, and it'll make a carbonate ion. But that's a relatively weak acid. It's not like hydrochloric acid or sulfuric acid that ionize almost completely in water. Carbonic acid is weak acid. And roughly speaking, the hydrogen ion concentration in a pure water system is about proportional to the square root of CO2. So if I increase CO2 from what it is today up to 10 times as much, the pH of water in equilibrium with that CO2, pure water, would drop by about a factor of 3 increase in carbonic acid or hydrogen ion, and about half a log unit change in pH. So going to higher CO2, first lesson is going to higher CO2 does increase your acidity some, but not dramatically. Okay, but it does matter because most soils, because of the decomposition of organic matter in soils and because of root respiration, have CO2 concentrations that are 5, 10, 20 times the atmospheric level. CO2 is, here, to put it in your context, the simple way to view CO2 concentrations in soil is exactly the same way as you look at the distribution of heat in the continental crust. You have a source term and you have diffusion out the top, and the equations are exactly the same. The length scale is 30 centimeters instead of 30 kilometers. Okay? So if you're familiar with that, you know how to do the soil CO2 problem. So you have production of soil CO2, you go down 20, 30 centimeters, you get a few thousand ppm, you get a boundary layer at 390, 400 at the top, it leaks out, right? But in the meantime, it makes the soil more acidic. But life is never that simple. This is an extremely simplified relationship. But what we often have in this terrestrial weathering environment are also organic acids. Here's a carboxylic acid, a really simple one, acetic acid. Has one of these carboxylate groups on it that pops up a hydrogen ion, leaving an acetate ion. And that's what it looks like. This guy here falls off. And so that can provide more acidity if you have organic matter. And also, it turns out the acetate ion isn't good at this, but some of the others, like citrate and oxalate, which are also common, and there's a whole bunch of others, they actually complex with things like aluminum and iron and actually substantially enhance their solubility. And so that's a big impact on the terrestrial environment. We won't spend too much time on that, but just so that you know. Okay, so then we have carbonate weathering and silicate weathering. And here's carbonate weathering. We take calcium carbonate, we react it with carbonic acid, we make calcium ion, and we make a couple bicarbonates. And so what we've done is we've consumed the acidity, and we've made bicarbonate. And and we've also made calcium. We refer to calcium, magnesium, sodium, potassium in the weathering literature is sometimes referred to as the base cations. And then that stuff is all soluble. It can go down to the ocean. And in the ocean, organisms takes the calcium and the bicarbonated carbonate ion and make calcium carbonate, and the reaction is reversed. So in the long run, nothing really happened. And on a time scale, a short time scale, this matters. But on a time scale, let's say 10,000 years, there's no net CO2 consumption here because there was a CO2 in the carbonic acid, and that's released back during the precipitation of calcium carbonate. So there's no net change in CO2. So weathering of carbonates is interesting for lots of reasons, but it doesn't have any long-term effect on the CO2 concentration of the ocean atmosphere system. But it's a very important buffer, and any rock that has any calcium carbonate will tend to buffer the pH pretty well. And so the pH of the ocean is about 8.3 because it's got calcium carbonate in it. So calcium carbonate is a really important buffer and is much more soluble and reacts much faster than the silicate rocks. It's also simpler. Silicate rocks, I could write 100 of these reactions, but here's a nice schematic one that does the trick. And here's anorthite, calcium plagioclase plus CO2, water. I can say water, or I can say CO2 and water or carbonic acid. Those are sort of equivalent statements. That reacts, makes calcium ion just like we had before, a base cation. It makes bicarbonate ion just like we had before, and it makes this aluminosilicate mineral here, which is a clay. That's a kaolinite. And so with aluminosilicate weathering, this is a little, yeah, okay. With aluminosilicate weathering, because the, is that better? Yeah. Okay.
To what extent does the CO2 in the set soils tend to track the atmospheric values? Are they fairly tightly correlated?
Not so much, because it really depends on the primary production of the plants growing in the soil. So there's actually a wide range depending upon what the organic carbon input to the soil is. So they don't need to track each other that closely. Yeah, and you can go and in different environments find quite different values. So they're always higher than atmospheric, or virtually always, but they can vary quite a bit. So there's not a close correlation to atmospheric CO2. And that's where the weathering takes place. So we don't expect really a direct effect of CO2 on weathering just by increasing the concentration, because it takes place in soils, and those are really controlled by biological processes rather than atmospheric chemistry. So anyway, making this clay is important because that's often the direct evidence of weathering that we have. And there's a bazillion different clays, and they all have obscure names, and we don't want to go there. But the net, when we go to the ocean, then we can precipitate the calcium and the bicarbonate back out. But we consume 2 CO2s there. We get 1 back. So we have 1 net loss of CO2 going into calcium carbonate as a result of weathering a calcium and magnesium silicate. So you take the fresh primary mineral, some CO2, some water, and in the end, after we go to the ocean and let the ocean and the ocean biology do its thing, we end up with calcium carbonate in the ocean, and we leave the clay mostly behind on the continents. And that's one of the things that goes into soils. So you can see that the key step here is making carbonate minerals in order to mineralize CO2, in order to take atmospheric CO2 or oceanic CO2 and turn it into a rock. That's basically what's happening here. And as even geophysicists will know, we don't make a lot of sodium and potassium carbonates in the world, except in places like Death Valley or something like that. So you really want to weather calcium and magnesium silicates to be an effective sink for CO2 long term. If you weather sodium and potassium silicates, there's a little bit of ion exchange, there's some other stuff, but by and large, they're inefficient sinks for carbon dioxide. Okay, so weathering does a lot of things, and here at the microscopic scale, this is from Puerto Rico, where there's a granitoid pluton weathering. These are little kaolinite flakes here. There's a scale bar at about 5 microns, so these are your clay minerals. That's a quartz grain there. And so there's a lot of mineral reactions actually occur, weathering reactions actually occur on mineral surfaces, and surface reactions are complicated. They're heterogeneous reactions in the language of physical chemistry, meaning they involve more than one phase. And so the surface environment is really interesting. This has bothered people for puzzled people for a long time. In recent years, there have been some advances using high-energy X-ray radiation, synchrotron source radiation, as well as molecular dynamics simulations to get a better idea. But basically, here's your solution, here's your mineral interface, and these are some different suggestions about what the structure of that looks like at the kind of nanometer scale, and that turns out to matter for weathering reactions quite a bit. Here are some molecular dynamics simulations of the interaction with water, this molecule there, with a SiO2, a quartz surface. And won't go through all this, but this basically is a molecular dynamics simulation of removing an SiO2 unit or an SiO4 unit to make silicic acid from that surface. That's something what they estimated based on these simulations what that looked like. And there's your length scale. It's a few nanometers, right? A few tens of angstroms, a few nanometers. So there's a lot that goes on there, and that's something that's an active area of research and very interesting in terms of how you bring things into that reaction zone, how you bring things out of that reaction zone, and what the structure of water is there. It's no longer liquid water when it's interacting strong with the surface, because mineral surfaces generally have charge, they're polar. Water molecules are polar, so they're oriented to one another, right? They're not randomly distributed. And in fact, modeling those surfaces is pretty hard, and mostly has been restricted to simple oxides like SiO2, and not so much on more complicated minerals. But anyway, from the microscopic and laboratory data, we have a few things. This is just a list, okay, of the things that control the rates of weathering reactions. And like I said, many things in the surface environment are out of equilibrium, and so we're fundamentally driven to deal with kinetics. There's a pretty damn good theory of thermodynamics. The theory of kinetics is not so good, and it's also much more difficult to apply to these kinds of systems because we generally don't know the fundamental reaction steps which are required to apply things like transition state theory in this kind of system. So we're stuck in this kind of nether regions of having a theory we can't really apply and needing a lot of empirical parameters in a complicated system. So it's a little ugly. But how far you are from equilibrium influences the rate. The diffusive transport to and from the mineral interface influences the rate. How many surface sites? You can imagine a checkerboard, and you only can react at the dark squares. Okay, and if those dark squares are mostly occupied by something else, your reaction rate slows. So surface site occupancy matters, and whether the occupancy is reversible or not. The defect density in crystal structures. The mineral surface area, which evolves substantially with the reaction. I'll show that in a minute. I already mentioned complexation, the fact that particularly some organic compounds can react very strongly with some of the constituents of the mineral lattice matters. Temperature, we'll see, is a big effect. Coatings of secondary minerals, pH, of course. Strain from the change in volume of secondary mineral formation, right? Just a certain amount of weathering. You've seen onion skin weathering in rocks. That basically is like it's like frost shattering, essentially. When you oxidize the iron and the micas, you tend to increase the volume and you spall off layers. And you have strain at a number of different levels in terms that it influences the rate of mineral degradation. And the permeability of the weathering zone, which evolves, and basically you get the idea. I could go on, and we could spend a month on each of these issues, right? So And so it's not easy to begin with the microscopic properties and really effectively predict the macroscopic behavior. There is a genre of work called reactive transport modeling that tries to do sort of apply a continuum assumption to, let's say, a soil or weathering profile, and use kinetic parameters to estimate mineral reaction rates, and then calculate volume changes and mass losses, and then recalculate the permeability and porosity, and so on. And that's an interesting thing to do, but it requires knowing a lot of parameters, which we often don't know very well. So it's an interesting approach, but there's only so much I think you can do with it. Here is an example of what some mineral weathering textures look like. Here's a pitted quartz grain. There's some more of that kaolinite. Here's a couple different feldspars that have undergone weathering in the soil in Puerto Rico. And you can see that the surface area is changing dramatically. And so as the surface area evolves, the weathering rate changes. As this all evolves, then the rate of percolation of water through the system changes. So these things matter, and they're not so easy to keep track of. One of the things that people have known for a long time, Arrhenius was a pretty important chemist in the 19th century. He's also the guy who kind of defined our modern greenhouse effect. And he understood something about climate and weathering back then. But it turns out that empirically, a lot of chemical reactions follow this kind of exponential dependence on temperature. And the key parameter is the exponential constant known as the activation energy. And so empirically in the laboratory, and you can derive this for some simple systems from theory, if you have monomineralic systems, you expect this kind of relationship. That 60 to 65 kilojoules per mole degree Kelvin for the value of EA implies a temperature sensitivity around 2.5 for a 10-degree temperature increase. Biologists do the same thing for biological reactions. They call it a Q10. How much does the reaction rate change for a 10-degree temperature change? This is sort of a linear approximation, right? Because we know the temperature on the Earth changes, but it only changes by a few tens of degrees maximum, right? So we can approximately get away with linearizing this not too badly. We don't really do that, but we could if we wanted to. Okay, so that observation has been around for a long time, and leads to this notion that, well, if weathering rates really can vary by a factor of 2 or 3 over reasonable temperature change, then maybe weathering rates should depend on climate in some way, and that might be interesting in a number of respects. So here's the basic idea, and this goes way back to the 19th century, and then was kind of put in a little bit more quantitative form, or substantially more quantitative form in the 1980s by people like Jim Walker and Bernard Lasager and Garrels, and it's something that has a lot of intellectual appeal, and there's a lot of reasons why we think it should be true, but we're still not completely sure exactly how this works. But for example, solar luminosity has increased about 25 or 30% over Earth history through the sort of normal stellar evolution. But liquid water we've had pretty much continuously present since at least 4 billion years ago, probably longer. And so it's the Goldilocks solution. How do we keep the planet from freezing over and staying that way? It may have frozen over briefly in the Neoproterozoic. It may, or at least substantially was frozen, but it never boiled off the oceans and became Venus. And yet the response time of CO2 in the atmosphere, and we've got CO2 coming out of volcanoes and other sources all the time, and the response time for that is on the order of 500,000 years, right? So 500,000, 1 million, 5 million, I don't really care. Over 4 billion, it's not significant. So what regulates the temperature over time if CO2 is constantly leaking out, and I can essentially double CO2 in a 500,000, 1 million year time scale, right? Or I can double CO2 in a couple of centuries if I build some power plants, right? So here's a thought experiment you're probably mostly familiar with. Okay, atmospheric CO2 increases, then atmospheric temperature should increase according to basic climate theory. Well, then the reaction rate for weathering should increase as a function of temperature just by the Arrhenius law, right? Also, the water cycle accelerates. The saturation vapor pressure of water is exponential in temperature. As we warm the ocean, we put a lot more water vapor into the atmosphere. Some of that comes down on land. And so if we get that, the CO2 consumption should be enhanced by these 2 points 2 and 3, and then that should pull CO2 back down, and the temperature decreases, and as the temperature decreases, the reaction rate should slow, the water cycle should slow down, et cetera, right? So we have a nice feedback system that should, in principle, buffer CO2 and climate through Earth history. And this roughly seems to work, right? But the issue is there's a whole bunch of stuff in like, well, water cycle accelerates. What does that do exactly to weathering? And we just looked at the complexity of those weathering profiles. Okay? And is the temperature effect in the field really what you see in simple laboratory experiments? And there's lots of reasons to believe it might not be that way. And of course, then, how does CO2 and water interact in the climate system? And also, we'll see that rock type matters, tectonic setting matters, what climate zone you're in matters, all of those things matter. And those are sort of geological factors or geodynamic factors, and so those are going to vary through time in Earth history. So we know climate has varied in Earth history, at least within some bounds, and we'd like to sort of put together, as Mark was trying to do, some kind of stories about how climate and CO2 and weathering and all that kind of stuff have varied. So how do we study weathering rates and processes at large scales? Because I've said it's pretty hard to go from the nanometer scale to the scale of the Amazon basin and do that very well. So one way is we can measure the dissolved flux exported by rivers. So this integrates over a wide area. We already talked about some of the sampling issues with zirconology, right? Water's a little bit different, but nevertheless you're integrating a whole bunch of processes upstream, even in a simple catchment. You saw that one soil profile I showed you. I've got n different weathering reactions going on within a few meters, and if I get some water that passes through that water, what am I seeing, right? It's a significant task to unravel that. So we can go up there and we can collect water, and we do get this integration, which is great. And John Edmund, may he rest in peace, I mean, he basically had the idea that if you went to the Amazon with one bottle of water that's 15% of the world's fresh water flux, you would, to a first approximation, know what the weathering was doing on Earth. And that John basically pursued a campaign of sampling the major rivers in the world and determining sort of global weathering fluxes on that basis. Right? And so, yeah, we can do that, and that's all fine. This is up in the wet part of Hawaii. I showed you the dry part before. And so this has been done by various people, and Jérôme Gaillardet at Paris has been a leader in this activity more recently. And so you say, well, what are the relationships between some of the large-scale variables and weathering rate? So these are relative chemical weathering rates here on some sort of log scale, although the scales vary a little bit. You can see there's a clear correlation between runoff and chemical weathering rate. Okay, so climate matters. It looks like the more rain you have, the more weathering you have. That kind of makes some sense, right? But these are mostly continental rivers, and we'll come back to some of the exceptions. It's not extremely obvious that relief really drives it. We see temperature. We see kind of two different groups here, and some of them have relatively low weathering rates despite high temperatures, and those are areas, some of those areas are cratons that have been weathered for a long time, like in Venezuela or in West Africa. They've had a long history of weathering, so the upper part of the system has been depleted in the weatherable elements, and now the weathering rates are relatively slow because there isn't that much more blood to squeeze out of the stone. Roberta?
How is the relative chemical weathering rate of silicates determined? What exactly is that parameter?
Okay, so that's basically what he's trying to do there is look at the flux per unit area, per unit time, right? So it's a sort of an area normalized flux, right? And so that the variations are maybe up to a factor of 100 in some cases, but that's kind of the extreme ends, right? And another thing that clearly plays a role is erosion rate seems to matter. As you erode more rock, you should make more surface area available, particularly fresh surface area, because if you don't make fresh surface area available, you weather that interface, it sits there, and now you've depleted the weatherable elements, not much will happen. So actually turning the surface over matters. So we've got not a very good correlation with relief in this data set, pretty good correlation with the runoff. A little bit ambiguous with temperature. If we subsample the data, we get a good correlation. If we include all the data, we don't, because there's multiple factors going on, and a reasonably good relationship with erosion. And so,
What temperature is that? Temperature of what?
That's the mean annual climate in the basin. Okay, and so that's related to the soil temperature, right? The soil temperature will vary on a diurnal basis because of diurnal heating. It'll vary on a daily. It's got multiple wavelengths in it, right? And you know about this is determining, glacier temperature, all that kind of stuff. So you've got a nice periodically forced boundary condition there. So soil temperatures in the upper meter or two where a lot of weathering takes place, so they tend to approach the mean temperature, let's say, of that on a monthly time scale.
This would be like a monthly
But these are mean annual, but depending where you are, right? If you're in Africa, the mean annual and the monthly is probably the same. If you're in Baffin Island, there's a difference, right? At least in Ithaca, where I'm from, there's a big difference, right? If you're in a temperate zone, you get a lot of variation. If you're in the Arctic, it's always cold. If you're in the tropics, it's always warm. And so the variation probably matters as well, right? So this is, I'm encapsulating a lot of physics, chemistry into little stuff here, right? I'm just trying to, These are mean annual temperatures, right, in the basin.
But with this strong exponential temperature dependence, it's not obvious that the mean temperature would be the appropriate.
No, and in fact, you're certainly going to see seasonality, and you see seasonality for two reasons. One is there's temperature variation, and the other is the hydrologic cycle is strongly seasonal in most places, and that's probably the dominant effect. Right? If you go to the Himalaya, you get a monsoon. Right? Guess where you get most of the weathering. Right? This isn't rocket science. Right? Go ahead. So some of these are, some of them are places where there's tropical cratons that have been stable for a long time. So like the Orinoco and the Congo and the lower Amazon, where that's been tectonically stable for a long time. It's been in a tropical weathering environment. So the weathering profiles there are very thick already. And so the reactive surface is down there tens of meters or even more and doesn't interact with the water very effectively. And so it's armored, essentially, which is why there's a relationship probably with erosion rate, because there you're getting rid of the soil cover and exposing new stuff to weathering on a regular basis. But it turns out that another Goldilocks solution is needed for that, too. The soup is either too cold or too hot, and we're looking for the soup to be just right, And if the erosion rate is very high, you transport material out of the basin before the chemical kinetics can catch up. So in places like the Himalaya, much of the sediment is exported and goes unweathered into the Indian Ocean. So we can pick up grains of sediment from the Indian Ocean, reconstruct the temperature of equilibration based on oxygen isotopes, and get a perfect metamorphic temperature of 450 degrees, even though the stuff has been transported 3,000 kilometers from its outcrop. Right? Chemically speaking, nothing happened. We had a big mass transfer event from a physical standpoint, but from a chemical standpoint, nothing happened. Now, that's not entirely true, right? But that's the trade-off, whether you're limited by the availability of fresh material on the one end, or whether you're limited by the transport of fresh material out so quickly you don't have a chance to catch up with it, and that's kinetically limited by the kinetics of weathering. So with carbonate minerals, limestones generally dissolve pretty darn quickly. So you don't export much detrital carbonate off the continent, right? You find a little bit here and there, some dolomite, right? But by and large, carbonates dissolve. Silicates partly dissolve and make clays, and some of that's exported, but part of that material is transported out without any chemical reaction because, roughly speaking, the reaction rates are about 6 orders of magnitude slower for silicates than they are for carbonates. I don't know, sort of, another one of these rules of thumb which is automatically wrong, right? Cinti.
Based on what you just said, why don't we see the chemical versus physical erosion plateau off?
Yep. We're coming to that. We do, in fact. That's why you're a smart guy, Cinti. You're one step ahead of the pack. So another way we can study this is, rather than to look at the catchment scale and integrate all those processes, is we can go to soil profiles. And so that can be more fun depending on who you put down in the soil pit. And so this is in Hawaii. This is in the Philippines. Again, we've got pretty extensive soil profiles around here. And I grew up in New England, and there was no such thing as a soil profile. It was a little bit of sand and gravel strewn across the landscape, and that's what they call soil. I had no idea. Right? I went to other parts of the world like, oh, okay, now I understand what they're talking about. And soil is sort of important because that's where we grow all our food. That's where all the terrestrial life is, right? This is kind of a big deal. So you can look at a profile, and you can look at these. And here's an example, again, from the site in Puerto Rico. And this is the mineralogy of that. So down here, this is about an 8 or 9 meter thick regolith, which is sort of a catch-all term. Sometimes people use soil a little more restrictively. This is the weathered zone. And so here we've got more or less fresh bedrock down here, more or less. And we've got about 8 meters of weathered material. And you got lots of plagioclase down there, and that immediately goes away in the weathering zone. The plagioclase drops down to very low values and then more or less disappears by the time to get to the surface. And you can see we wrote that weathering reaction. We said plagioclase turns into clay kaolinite. Boom, the kaolinite goes way up, and there you go, right? And we've got quartz, which doesn't react very fast and kind of sits there. It doesn't really change very much. And it turns out some of the micas are relatively stable as well, don't react too fast. This biotite is reacting but it's only partially reacting and it's not completely going away. We get some iron oxide buildup. So that's sort of the mineralogy of the kind of thing you expect to see, right? And then in the very top part, you've actually got biological activity in the soil, and that screws up some of the elemental compositions because the plants pump up lots of elements and then return them to the soil. So plant activity actually impacts the soil composition in the uppermost part pretty significantly. But you can see that rooting zone only goes down a meter or so. In a lot of soils or tropical soils, it only goes down 20 or 30 centimeters because there's no interest in the plants going deeper than that. All right, this is a way that we can look at this elemental mass transfer. We normalize to some sort of immobile element because soils are open. We've got dust coming in, plant material, dead chipmunks, and we've got mass losses going out, all that kind of stuff. So it's a very open system, so how do you know who's coming and going? If you simply see the fact that the concentration of an element increased, did that element increase or did all the other elements decrease, leaving a residual concentration in the line? People in California know about this. It's called a placer gold deposit, right? So one trick that's been reinvented many times over the years, goes back to the 1840s, is to normalize to an element you think is not moving in or out significantly. In this case, I think this is done to zirconium or niobium. Usually one of these refractory high field strength elements are relatively immobile in the environment. In these really weathered environments, you actually have to test that because you'd be surprised how much hafnium and zirconium and thorium can move around in the presence of organic ligands when the soil pH is 3.5, right? But in this case, this is an example. So this tau function basically is 0 when there's no change, and it's -1 when there's complete loss. And if you have addition, in this case, none of these elements show addition, but if we put carbon in there, we'd see addition of carbon in the upper part of the soil, right? So it can be either positive or negative. For the rock-derived elements, it's usually negative. And you can see here on this side, the sodium and calcium are out of there almost immediately. They're completely depleted. Magnesium is substantially depleted, but some is left in the biotites. The silicon is about half depleted, and then iron and aluminum tend to be less so because they're less soluble, right? And this varies a lot in soils. This is a pretty weathered soil, so it's going to depend where you go. Here's an example of how this affects the hydrologic behavior. Down here in the bedrock, you're primarily controlled by fracture porosity. Right? The permeability of solid granite is pretty darn low, at least on our time scale. So you've got fracture porosity, which allows some permeability in the system there. But as you weather, you open up that porosity. And, of course, up in here, we've got bioturbation and organic matter. The porosity goes way up. So the porosity is related to the permeability in some way that's complicated, but clearly they should be related. And the permeability controls sort of the Darcy flow of the water through the system. So as the porosity varies, and we've already shown how the mineral surface area varies, right, the reactivity of the system is evolving constantly, which is why this is a tricky thing to deal with. So, okay. So here is some data from Cliff Reby and Jim Kirchner, where they, about a decade ago, did some interesting stuff. And they essentially looked at chemical weathering rate by using plots like I just showed, looking at the depletion index of the elements of interest. And then they used cosmogenic nuclides and assumed a steady state denudation rate. Right? So they said, okay, we're going to go to places where we think the short-term denudation is approximately in steady state and use cosmogenic nuclides, beryllium-10, aluminum-26, to estimate that. So they got a denudation rate of the surface versus a chemical weathering rate, a bunch of different granitoids around North America, I don't know where all else. And you can see there's a pretty good correlation here, right? Chemical weathering rate in their study scaled pretty well with denudation. So that poses an issue, and this has been brought up a number of times, probably most famously by Ramo and Ruddiman, who argued based on surrounding isotope ratios that the real controller of global weathering rates was tectonics, and climate was secondary. And if that's true, you go, wait a second, what stabilizes the system? Because tectonic events are probably not going to happen in any particularly organized way to help you stabilize your climate, right? But clearly, there are a number of data sets that show this relationship to erosion or denudation or whatever you have pretty clearly, and so that's something that can't be ignored on the altar of some theory just because the theory is nice. And so here's their same data set, chemical weathering rate as a function of mean annual precipitation. That's pretty much of a mess. Mean annual temperature, that's kind of a mess, right? And they, from their data, they would estimate an activation energy about much less. Remember before we looked at the data for the feldspars that gave the sort of factor of 2, factor of 3 increase in weathering rate for 10-degree temperature increase. They got a much lower exponential constant, the equivalent of that, which would imply weak temperature sensitivity to weathering in these kind of continental granitoids. And so, basically this kind of study and some others don't strongly support the idea of a climate weathering feedback in these settings. Right? So then you go, okay, what's up with that? These are primarily granitoids from the United States and in different climate settings. Another way to get at weathering rates globally is to look at tracer studies. Okay, here's the strontium isotope signature of seawater over the last 65 million years in some crude way. There's the osmium isotope signature of seawater in the last 65 million years. This is the data that made Ramo and Ruddiman say, geez, global weathering rates have gone way up because continental strontium is radiogenic, mantle strontium is unradiogenic. So if you shift from away from mantle values towards continental values, then presumably you have more input. And you see this in osmium and all that kind of stuff. And I could go on for the rest of the day just on this alone, but as a cautionary note, having spent a good part of my life doing tracer geochemistry, right? What tracers trace is the element that the tracer is made out of. So it doesn't matter if it's strontium isotopes or osmium isotopes or polonium-polonium ratios. What you're tracing is the polonium, not the continental weathering rate. So you have just a tiny leap of logic to go from the polonium flux to the continental weathering rate. Okay, those are two different things. And you hope that the polonium-polonium ratio gives you information about the continental weathering rate, but it's never simple. And we now know why these are so anomalous in the late Cenozoic, and it turns out neither of them are associated with big increases in weathering rate. There may have been big increases in weathering rate, but this isn't evidence for it. Okay, so that's a big issue. Roberta. We're leading up to lunch here, aren't we? I mean, it just doesn't matter, right? And it turns out there's been recent work, of course, of some of the stable isotopes of the major elements, silicon, magnesium, calcium, which there you're actually getting to what you really want. You hope that strontium has something to do with calcium. I don't know what you hope or osmium has something to do with, but osmium has something to do with what? Anyway, and you can look at these. And so, but it turns out the variations in calcium, magnesium, and silicon in these environments are A small, B substantially complicated by biology, and in the case of calcium isotopes, you look at the calcium isotope records over the last 25 or 30 million years from the different groups that have done this, and they simply don't agree. The resolution is not there to resolve a temporal trend right now. Each group thinks they've done it right, but when you lay them all on top of each other, you just go. And Don DePaulo is probably going to come in here and throw something at me. But anyway, wouldn't be the first time. Yes?
Are you going to tell us the answer?
To what?
You said that people now understand why this is changing, even though weather rates.
Okay, very quickly, I'm going to draw this. Can I draw this? Because it's just easier to draw it than to explain it. Very quickly, globally in rivers, if you look at strontium concentration, I'll do reciprocal concentration because that's what geochemists do, just to confuse the innocent, right? Can you see this at all? That was a bad idea. Try it this way. Okay, so basically, so this is going to be high concentration down here, and that's low concentration down in there. So in most world river systems, you either have old cratonic basement, which has got low strontium concentrations and is very radiogenic because it's been sitting around for a long time, or you have, in many cases, carbonates dominating your flux, which have lots of strontium, dissolve easily, and have unradiogenic ratios, right? The Himalaya, because of metamorphism, of recent metamorphism, have homogenized that signal. So they've taken the radiogenic strontium out of old rocks during recent metamorphism in the last couple of 20, 30 million years, have moved that into highly weatherable silicates and even limestones. There are basically dolostones in the Himalaya that have a strontium 87-86 ratios of 0.8 that we've worked on. You don't need a mass spectrometer. All you need is an analytical balance at that point. And so the Himalaya lie up here. And because of this recent metamorphic history, they're vastly anomalous with respect to strontium isotopes. But it turns out because of that transport, kinetic limited weathering, they're not really anomalous in terms of the weathering flux. So, and for osmium basically traces black shale weathering. So you have a few horizons of black shales that are absurdly rich in osmium, absurdly radiogenic, and you have those in the Lesser Himalaya, and that is at least part of that story. Although among the osmium aficionados, there are big fights about what is, in the big picture, a small issue, right? The smaller the issue, the more intense the argument, right? And so that's why the tracer studies have to be really filtered through a lot of thinking. Here, yep.
So basically, what you're saying is that the rise that we see in both strontium and osmium is likely related to the Himalayas, but it's not necessarily because of the exposure of these unusual rocks.
Yep.
But it's not necessarily related to the weathering flux.
Exactly, yes. And thanks for making me clarify that. So here's or clarifying it for me, which would be a better way of putting it. Here's the deal. We now have pretty good records on CO2 in through the Cenozoic from various proxy methods, right? And from Mark Pagani and Kate Freeman and boron and la-di-da. And so basically over the last 35 or so million years, they agree pretty well, and our last 50 million years roughly agree. You had high CO2 back here in the Eocene. It was warm. Ben can tell you all about this. It cooled off. CO2 fell. Antarctica glaciated at 34.5 million years. And CO2 has been relatively stable and relatively low since then. There have been some variations between about 250 and 400 ppm. But back here it was probably over 1,000 ppm. It's not really clear what. And, of course, we've had ice on the planet since then. So CO2 doesn't vary much through the last 25 million years. But look at the isotope tracers. They go bonkers, right? And so the climate had cooled, basically. It cooled further going into the Pleistocene. But the climate had basically cooled. The CO2 had basically fallen before this real rapid acceleration of strontium, before this begins at about 16 million years here and takes off like that. So, in a sense, regardless of whether I understand the tracers or not, we know from the PCO2 and climate records that the main Cenozoic cooling event, and also the CCD, the amount of carbonate accumulating in the ocean, also increases in interval. It's telling you more weathering is on land. So whatever was really happening in the Cenozoic, the big story is the Eocene-Oligocene transition, not in the Miocene to Pliocene in terms of weathering. Now, it doesn't mean there's nothing that's happened since, and that's the big story. Here's the diagram Sinti was constructing in his head. This is a more recent compilation. Again, weathering rate in tons per kilometer squared per year versus erosion rate based on both river dissolved data and regolith depletion data. And you can see as erosion rates get high, it flattens out. And the regolith data don't really see that because the cosmogenics don't work well with denudation rates are really high. Basically, they get maxed out. So we it's gotten a little better as the techniques have improved. And a number of years ago, we tried this in the Himalaya, and basically the rocks are sitting at the surface for such a short period of time, they don't interact with any cosmic rays, and so nothing happens, So you don't get much where the erosion rates are really high. So anyway, yeah, it does roll over, right? But clearly erosion rate matters in continental settings a lot. And we still have this issue, though, where the climate sensitivity of continental weathering, of granitoid weathering, for example, doesn't seem to be that strong. It's there, but it's also clearly confounded by tectonics. And then you start thinking, well, what other parts of the story matter? And so I'm going to argue today that we have volcanic weathering is an important thing, and not something that you can kind of understand from a sort of not first principles, that's the wrong idea, but you can sit down and think this one through and say, well, geez, it ought to matter, let's go see. And so volcanics, and arcs in particular, they have calcium magnesium-rich compositions, which, for example, the Himalaya don't. So the Himalaya are a lousy sink for CO2. And volcanic rocks generally do, and so that's good. The weathering is much faster in volcanic rocks, partly because the minerals, the calcium magnesium-rich minerals, dissolve faster, react faster than the potassium and sodium-rich ones, and partly because of textural features. Glass and stuff like that is very reactive. These arcs are by definition tectonically active. They're almost by definition wet. They're all sitting in the ocean. You put topography in the ocean, you're going to be wet. That's simple climate physics. That's probably true throughout Earth history. They have high erosion rates because they have steep topography and they're wet. And that will pretty much guarantee you high erosion rates and weak rocks, right? And they're frequently resurfaced either by erosion or by new eruptions, right? So this ought to be the perfect storm. And the question is there any sort of climate sensitivity? So John Milliman has spent a large part of the second half of his career compiling sedimentation rates globally. And sediment yields from, let's say, Western Oceania are at least an order of magnitude greater than the global average. A lot of sediment is coming off these areas, even though They're not that large. And let's look at, there's a composite mean annual runoff map for the globe. This is basically telling you the blue is really wet, white is where it's really dry. And so right now, a lot of that material sits in the wet zone. Of course, the latitudinal distribution of rainfall is perturbed by topography, like Tibet. So you have a lot of wet up there, which should be in the horse latitudes. And so topography and climate interact in different ways. Here you've got a lot of wet in the Amazon basin, but that's that area that's really flat and not much weathering takes place because it's been weathered for so long that there's not much left to come out of there. The same is true in the Congo, Zaire basins, for example. But we got a lot of water coming in there, and we have the right kind of rocks. We also have wet zones all around the Pacific Rim, but of course it's colder up here than it is down here, and if temperature matters, we might see that, right? So we're going to see if we can see anything. This is just a zonally average runoff. So you can see there's a lot of runoff at the equator. You knew that. There's a lot of runoff at 45, 50 degrees latitude in terms of millimeters a year, but there's no land area down there. So that peak is totally misleading. This is like Patagonia. So Patagonia is really wet, right? But who cares, unless you're trying to go there. So there's no land area to do anything down there. So here's the global. This is just a super classic paper that John Milliman wrote. Now this is 30 years ago. Geez, I was an undergraduate or something. But anyway, so sediment fluxes. So they're huge off of Oceania, off of Southeast Asia and the Himalayas. They're kind of significant off of parts of Alaska. They're pretty good off of South America because the Orinoco and the Amazon are basically the two biggest rivers. That's about 20% of the fresh water flux. But most of that sediment is actually derived from the eastern slope of the Andes there. And so it's not derived from the basin out there. But that's where your big sediment fluxes are, right, currently. And the rest of it just doesn't. Look at the Mississippi. We think of the Mississippi as a big river, right? But when the Mississippi was in the huge flood in, 1992 or something like that, it was at something like 10 to 15,000 cubic meters a second. This is like the biggest flood ever. This is what the Brahmaputra does sort of in a weak monsoon season. In 1998, the Brahmaputra alone hit 100,000 cubic meters a second during the monsoon. And 60% of the country went underwater. So these areas, this is where most of the fresh water comes off here, and most of the sediment comes off there. And the rest of the world is not important. Roughly. Right? So let's compare the chemistry of some Himalayan rivers. This is some of our data from the Himalayas. You can see relatively low silica concentrations and low calcium and magnesium concentrations. And we try to correct for just the silica component, and we may have missed a few in there, but yeah, maybe some of that's real. And then the blue data are from the Philippines, and the green data are from Hawaii. You can see there's just a lot more solutes and that kind of stuff. Right? These are and the Hawaii has got a special story that goes with it that probably applies to the Philippines too, but we don't know yet. So those data are from the island of Luzon, the northernmost major island of the Philippine chain. That's the plate convergence. This is a place that's dominated by the water cycle is dominated by typhoons, and so we sampled a bunch of areas where we were in pretty much only volcanic catchments. And of course, that's Pinatubo. Probably used to look like that, right? And what year did Pinatubo erupt? 90? 92. Okay. How many of you were born then? Almost everybody, yeah. How many actually remember it? It was kind of a big deal, but it's pretty cool to go there. Anyway, this is a river that you're seeing, right? And this river channel, I don't really have a good picture, but this river channel here is probably 2 kilometers across, and there was hardly any water during the dry season, and it's filled with white pumice. It's blindingly white in the tropical sun. So that water is basically now groundwater, and we're not even seeing what goes on there. So it's full of white pumice, and I've done field work in the tropics, and you're working by the side of the river, you're getting some water samples, if something floats by, and if you know it's good for you, you don't pay too much attention, right? But something caught my eye about what's flowing. You work in India, and you work in South Asia, and all, you don't want to look, right? So, but this caught my eye as sort of something was different about it, right? Being, unfortunately, an aficionado of things floating in rivers in this part of the world, these parts of the world. And it turns out these are pieces of pumice floating down the river. So guess what's going to weather fast, right? So that kind of stuff, the textural stuff in volcanic settings probably matters a lot. Okay. Another thing, back to the strontium question. Well, if we do have high weathering rates and high CO2 consumption rates in arcs, right, but it's associated with, the classic story has been when the strontium isotope ratio of seawater goes up, there must be more weathering on land to drive that, right? And that may be true with respect to radiogenic strontium, but radiogenic strontium does not represent CO2 consumption. So if we look at CO2 consumption, or strontium, we can say, okay, what's going to drive the strontium change in the ocean is the difference between the input and the seawater multiplied by the concentration, right? So if the river inputs are the same as seawater, it doesn't matter how much strontium you put in, you're not going to change it. If they're more radiogenic, it's going to make it go up. If they're less radiogenic, it's going to make it go down. All right? And so then we can make a quick chart of that just to see kind of schematically what it looks like. So there's my whatever function, trident function. What do you call those things? Major rivers in the world, many of them are more radiogenic than seawater. In case some of the Himalayan rivers, way more radiogenic than seawater, but they have relatively low CO2 consumption rates on an areal average basis. If you look at some of the data from the Philippines and Indonesia and Hawaii, they make seawater go down in 87, 86 because they have ratios like 704 or whatever, and yet they have much higher CO2 consumptions per unit area. So basically my argument for a long time, and people are starting to listen, is that the 87-86 ratio and CO2 consumption, everybody's had it backwards for a long time. And you know that's like most things. It's likely to be sometimes true. So anyway, this is tropical arcs have CO2 consumption, 6 to 10 times the global mean, and we'll look at this a little bit more. But we saw that before. We had Himalayan data. We've got Kamchatka data in here as well. Kamchatka is a lot colder than the Philippines or Hawaii, or the Antilles, excuse me, in this case, not Hawaii, but same idea. And so you can see that weathering rates in Kamchatka look a little bit slower than they do in the warm region. So that's a little comforting. Maybe we're going to see some climate feedback. Okay, but these are areas that are pretty strongly undersampled because people like John Edmund, Jérôme Gaillardet sensibly went around and sampled the biggest rivers in the world because they want to get most of the water flux. All right, how many of you can name one river in the Philippines? How many of you can name one river in Indonesia? All right, they're all small, right? And so you miss it. If you sample the 25 or 50 or 100 biggest rivers in the world, you might catch one of those, okay? So it's the sampling problem, right? And so it's a non-point source problem, right? You got lots of little rivers, and they're a pain to get to. And they're hydrologically, small rivers are very variable. Big rivers, the discharge goes up when it's wet and goes down slowly when it dries out. Small rivers go boom in 24 hours, and they go back down in 48 hours. And so the discharge can vary by a factor of between 10 and 100 on a time scale of 2 or 3 days. And so if you miss that, you've missed most of the discharge. You also may have saved your life, but you've missed the sampling opportunity, right? And so that's the problem. Another issue that goes into this is something that we kind of, when it's one of those things that you find, you go, boy, we were stupid. Why didn't we think of this before? Here's Hawaii, a little image of Hawaii. And it turns out the Hawaiian surface shows this dramatic topographic evolution in time. The Kilauea is the active volcano. Mauna Loa is last erupted in 1984, so we basically call it active. Mauna Kea hasn't erupted in a few thousand years, and the main eruption stages were over 30, 40, 50,000 years ago. Kohala was active a few 100,000 years ago. Probably the last significant activity there was 150,000 years. This is the windward side. That's the leeward side. That's where all the hotels are over in there, where there's some beaches. There's not big beaches on Hawaii because it's too young, but there are some nice ones. And so the wind comes in there, and orographic uplift, you get a lot of precipitation in this side. You can get up to 4 or 5 meters a year of precipitation. I don't know what the annual rainfall in Berkeley is. What is it? Probably 40, 50 centimeters, something like that. Geophysicists are hopeless. It's a meter in Ithaca, which we think of as a moderately wet spot, right? So we have 4 or 5 meters of rainfall on this belt, something like this. But if you go on to Kilauea and Mauna Loa, there's no surface runoff. There are no permanent streams, and very few streams that even run intermittently, because this thing is a hydrologic sponge. Some of you know Bob Berner. He went out to work in Hawaii. He was interested. He came back, there's no goddamn hydrology in Hawaii, because he wanted to look at streams draining young volcanics. Well, the problem is there's plenty of young volcanics, but there were no streams. So he took that, as Bob would, as a personal affront, right? It would. So anyway, we get into this intermediate age surface of Mauna Kea, let's say 50,000 years plus minus. You can see these are profiles. This is looking at the topography along this line at 500 meters and 200 meters above sea level. You can see you're basically seeing the constructional volcanic topography on Kilauea and Mauna Loa. Here you begin to see some incision into the Mauna Kea surface, and here you see deep incision, canyons up to 1,000 meters deep on the Kohala surface, partly because there's a giant landslide there. And that's what the topography of Kohala looks like. And you have waterfalls that plunge 300 meters free fall into the pools and all that. It's pretty damn cool. But anyway, what's happening, we believe, is that as we develop a soil profile, in the case of volcanic rocks, it goes the other way around. In normal rocks, you weather them, the soils tend to get more permeable. In volcanics, they're so permeable, you have lava tubes that you can drive a truck through in Hawaii, right? Literally. And in volcanics, they get less permeable as you develop a clay-rich soil layer. And so instead of all the water percolating down directly, it begins to move laterally. It initially is organized according to a little volcanic topography, and then it begins to incise. And then it incises deeper here, especially when we have a collapse event, and now we have big hanging valleys, just like Yosemite here, except for a different reason. And so that turns out to matter, and when we looked at that kind of stuff, we realized that in these kind of streams here, we're seeing some weathering, but we looked at these streams that cut deeply into the edifice, and we realized that the streams up here had nothing dissolved in them because it's all highly weathered, and here they were quite concentrated. And groundwater is going down through the volcanic pile, being sampled by these streams and coming out. And so we then embarked on a campaign of looking at groundwater through wells and stuff like that. And we found in Hawaii that alkalinity, which is a measure of CO2 consumption, and silica were about 3 or 4 times higher in groundwater than they were in stream water. And on the island of Hawaii, there's about 3 times more groundwater directly discharging to the ocean in freshwater springs at the coast than there is stream runoff. So you multiply 4 times 4 and you get 16. So basically the weathering, there's 15 times more weathering fluxes being exported to the ocean from the island of Hawaii via direct groundwater inputs than there are stream water. So we spent a lot of time measuring stream waters, and we were barking up the less than 10% tree. But it was fun. It didn't actually get us very far, but yeah. Not so much, right? We can only guess at that at this point. That's something we're trying to think of ways to get at. But we can talk about that. As these waters have a long residence time in groundwater, and we think they have a reasonably long residence time, they should sort of approach saturation with the mineral assemblage, right? So it's unclear how far that front has propagated in, right? It might be that the water travels 1,000 meters deep, but maybe it becomes sort of saturated with the local mineral assemblage after, I don't know, pick a number, 400 meters, I have no idea. But it's an interesting question, right? So this idea of deep weathering, this is one of the clues to that. So anyway, back to this idea that maybe we've got some temperature sensitivity or climate sensitivity in this stuff. So weathering in these basaltic provinces, this is some data compiled by Chiline Desser and Jérôme Gaillardet. And if you ignore Iceland, which is cold, and these other places are mostly warmer, there's a reasonable correlation between the CO2 uptake flux and runoff. All right, R squared of 0.6, and geochemistry is not bad unless you're trying to do isochron stuff. And but in this kind of stuff, where we're integrating lots of different places, that's not too bad if we keep Iceland out of the mix. And then if we look at temperature, and again, we remove the areas that are very arid and very water limited. So if you go to the Afar Triangle, for example, you've got basalts and it should weather, but it doesn't ever rain there. So we put that one down here someplace because nothing happens. And you can see there's a reasonable exponential fit. And that corresponds to an activation energy of about, in this particular fit, which, this is not ready for prime time, okay? This is not published because it involves, a little bit of this here. But hopefully we'll get some data where we can really do this. Okay, but here we ended up with an activation energy about 56 kilojoules a mole. I said the experimental data on feldspars that indicated, a factor of 2 to 3 temperature dependence or 10 degrees was 60 to 65. So we're really right in that ballpark where we would expect, if this is appropriate, that volcanics should show an approximate doubling of weathering rate with temperature, that they actually do that in the field, not just in the laboratory. Granites do it in the laboratory, they don't do it in the field. Basalts do it in the field. That matters. Okay, they actually do it when you go out and hunt basalts with your basalt hunting rifle. So that's looking pretty promising. But the issue is volcanics are a relatively small amount of the terrestrial surface, right? And so we have high water fluxes, high solute fluxes. And so what we find for tropical arcs is something like 1% of the terrestrial surface is accounting for at least 15 or 20% of the carbon consumption due to silicate weathering. All right? And that doesn't include some other areas which might be involved, and obviously not all volcanics are in arcs. But those happen to be good. We're not really taking into account geothermal fluxes, basically because you have volcanic active volcanism. You get water reacting with rocks at much higher temperature, and those reactions are much faster because of the same kinetic relationship. We're worried about whether it changes over 5 or 10 degrees. Well, if you crank up the water temperature to 150, your reactions go. Okay, that works really well. And we really don't have an idea of groundwater fluxes any place but Hawaii. In Hawaii, we see they're an order of magnitude greater. All right, so I could take all these factors and I could end up with 300% of global CO2 consumption, right? Obviously, that's wrong, right? But I think this number is not an overestimate, okay? And so then the issue is, or the hypothesis is that arcs and also to some extent large igneous provinces, when they're in the right spot, could be the locus of the climate weathering feedback. You don't need to have the entire planet be strongly sensitive to climate to regulate CO2. You have weak sensitivity in the cratonic setting, but it's not zero. You have some tectonic sensitivity there as well via erosion rates. But maybe the main place where you find the climate sensitivity that helps regulate planetary temperature over long term is in settings where you have volcanic rocks, particularly arcs, because they combine volcanic rocks and water. And you got to have water, right? If you're dry, nothing really happens. So the Deccan doesn't weather that fast because it's dry, for example. Siberian traps don't weather that fast because it's really cold. Okay, and one of the things I'm hoping to do with the new geoprisms move into the Aleutians is try and get a good first-order study of weathering rates at the Aleutians. There's some data from Kamchatka that are okay, some data from the Philippines, pretty good. At least I think so. I think we did a good job. There's some data from Indonesia that's not bad. It's similar to the Philippines and the Antilles. Good data set. So we've got the warm end kind of figured out. The cold end we don't have figured out too well. So what I'd like to do is march up the Pacific Rim from the equator to the Aleutians and see, is there really the climate sensitivity to weathering that we really think we've found, right? And actually get some real data behind this. So that remains to be seen, right? But so that's one idea. And so the interesting thing for this group is that a lot of you guys know more about arcs than I do, at least how they're made and where we might find them in different times and all that kind of stuff. So looking through Earth history, the abundance and position of arcs and large igneous provinces might be important drivers of climate. I'm not the first person to say that, and I think Mark alluded to that yesterday, right? But we in particular have, I think, provided some data to really, some of these ideas have been around for a while, but you actually need some data to demonstrate it. Sinti.
Yeah, just a comment related to that. I mean, Bob Stern will be here, and he may say something about the Western Pacific zones, but there was a fundamental shift 50 million years ago. Tonga, Kermadec, all of those
Right.
island arcs, so it kind of supports the...
Yeah, and I think there's a lot of, at the moment, there's a lot of just so stories you can make, right? And they might, some of them are probably even true. But the issue is, what can you do about this to kind of nail it down? Because we've seen there's a lot of feedbacks here, right? These are strongly feedback-controlled systems, so you can pretty easily tie yourself in knots with the feedbacks. And so this is an occasion where, let's say I was talking about the value of models the other day. Okay, for me, I find the value of models, I get some notion in my head, that we had some event here, and this rock type came up, and the polonium-bolonium ratio is telling me whatever, and I can make a big story. So I got to write down some equations and do the numbers to see if this makes any sense or not. And I have to not forget too many terms, right? Because you can talk yourself into anything, and unfortunately, there's a long history in this part of the geochemical community of telling fairy tales that sometimes they're even true, but if you don't actually make some attempt to quantify it, you're sort of screwing around. And not only that, but chances are you're going to be wrong, because there's enough feedbacks and complications that you kind of need to write down some numbers to be able to do something with it. Bill. Oh, no, not Bill. I'm sorry. I couldn't see. I had the lights in my eyes.
So when you talk about arcs and this is all, got a probably relatively long time scale, right?
Yeah.
I was kind of curious, how about the glaciation, deglaciation?
that's an interesting issue, and the global landscape is substantially perturbed by Pleistocene glaciation, right? We've scraped all the cover off of, Canada, for example, down to fresh rock. So all that sediment that used to be there a couple million years ago is gone. We've created lists all over the place. It's nicely fine-grained stuff. It weathers well. It makes a great nutrient source for plants. All of the great grain belts in the world are basically on most of them are on list deposits, right? The upper Midwest, the Czechoslovakia into the Ukraine, northern Europe. These are all lissic soils to some degree, or many of them are. So there you do, but it probably does to some degree perturb weathering rates. But much of that material is still a relatively inefficient sink for CO2 because it's not the calcium and magnesium rich silicates, and that seems to matter. The key thing that makes you think about this is we simply don't make sodium and potassium carbonates in the ocean. We have some ion exchange, a little bit of uptake of sodium by the oceanic crust to make spillites. If you're, Rick and I were joking about, how many of you have never heard of a spillite, right? Everybody knows what a spillite is. Raise their hand. Like I said, okay? That's sodic alteration of the oceanic crust, right? You take up some sodium, you kick out some calcium. So there's things like that, but they're not major, right? And so sodium and potassium probably get removed from the ocean. They have very long residence times, order of tens of millions of years, right? Joly used the salt content of the ocean to estimate the age of the Earth back in the 19th century, and he came up with an estimate of the age of the Earth of about 100 million years. And his calculation was absolutely correct. He looked at the mean salt content of rivers going in. He looked at the salt content of the oceans. He said, if we start with distilled water, how long does it take to reach the salinity? He got 100 million years. So his calculation was correct, but the interpretation was wrong. He wasn't calculating the age of the Earth. He was calculating the mean residence time of salt in the ocean. And for chloride, the modern estimate is like 70 million years. He did a pretty good job. He just he answered the wrong question, or he answered the right question. He didn't know it. So those are probably removed by evaporite formation and stuff like that, rather than fluid rock interaction in most cases.
I was just going to ask, what is the main sink for sodium?
Yeah, evaporates is the main sink. It's not a steady state with such a long residence time. If you put salt on the roads, you could do that for a million years, and you'd have no change in the sodium concentration of the ocean because it's so large, right? So it's not a steady state. So probably episodic, plate tectonically driven things like the Permian salt basins take most of it out. And Bill Hay has looked at the evolution of salinity in the ocean over time based on that kind of approach. So, there's some removal and some ion exchange that actually does interact with the carbon cycle. It's not zero, but it's not the main thing there. So anyway, that's a couple things to think about. And let's see. Yeah. By the way, right, arcs make CO2, right? And so then all of a sudden we've got another whole slew of feedbacks. If the place where much of the CO2 is being removed is also the place where a lot of the CO2 is being generated, this starts to make me really kind of have to think even harder, which I usually, I learned from a math professor at Harvard that all the ways to avoid actually thinking, because almost nothing is more painful than actual thinking, right? Answer some email, arrange your desk, go for a run, have a cup of coffee, now it's pretty much time to go home. I was able to do all this work all day long and didn't have to think at all. So, it's great. And so this is the kind of stuff that you have to worry about, right? So maybe in the after lunch part, we'll come back a little bit to this and a little bit of what's going on with the oceanic crust and arc, because I haven't talked about the oceanic crust. The oceanic crust is also a sink because we alter the oceanic crust. And that altered oceanic crust contains a lot more carbon than juvenile oceanic crust because of carbonate veining and some organic carbon deposition in there, and then, of course, a sedimentary cover on top of it. So that's another story. We've only talked about the terrestrial surface. And we'll talk briefly about why the terrestrial surface is likely to could potentially have a strong climate feedback, whereas altering the oceanic crust is likely to be much less sensitive to climate. That's a little bit of a chemistry question, which I won't spend a lot of time on because not all of you are that fascinated by alkalinity budgets and stuff like that. So I'll spare you most of that on a Friday afternoon, but if anybody wants to talk to me about that in a little more detail, I'd be happy. I know Jim is a big fan of alkalinity budgets, so we can have lunch, okay? Anyway, so that's a little bit. Weathering it's a complex animal. It's a big subject, and it involves everything from high-tech material science techniques applied at the nanoscale to relatively complex chemical reaction modeling, which is some of that was born here at Berkeley. But that's a complex subject in itself. And then these large-scale things. So I'm not trying to, this is by no means a representative. This is a bias sampling of what weathering looks like. But anyway, that I think, I'll just take questions. So, Roberta.
Has anybody looked at the Hawaiian deep drill cores to see what kind of weathering horizons exist in those? And can you get from that a handle on how deep the weathering goes? I mean, obviously you're going to have resurfacing because of constant lava flows coming out.
Yep.
And difficult to work out exactly how deep the weathering goes.
Yeah. Roberta's asking. There was a continental drilling project core that went in by the airport in Hilo into young Kilauea Mauna Loa flows and went, I don't know how deep it went, a few thousand feet, right? I don't remember. So they haven't done too much on that. Mark Conrad, who was at Lawrence Berkeley here, did some work on that, looking at oxygen isotope. Not a lot has been done on that, so that's sort of on the to-do list. There's clearly hydrothermal alteration in there, though. Right? As you go down, the water gets warmer, and then it gets colder again. You get seawater entrained. And typically in these continental geothermal systems, you think of them getting hotter as you go down, right? But in fact, often the fluid motion advects cold water into the side. So it's not uncommon to drill into a geothermal system that's hot at the surface, and you go down, it actually gets colder because the advection of cold water in from the side, right? So that is an interesting question. I think that would largely give us information on the hydrothermal alteration in the youngest stages rather than the longer-term weathering story, though, because of that, because it's so immature still. But it is something that, that's something that needs to be looked at, and I've been thinking about that, and it's just one of those things I haven't got around to. I've talked to Mark about it some, and I was supposed to talk to so-and-so at UH Hilo, and I didn't get around to it when I was out there last month. You know how it goes. Other questions? Yes, Barbara.
Back to something you said, maybe I missed it, but you said that basalts behave the same way in the field as in the lab, but not granite?
Yeah, because if you look at if you take feldspars from a granite, or ones that you make, and you put them in a beaker in the laboratory, and you look at the weathering at the rate of dissolution, you find this relatively strong temperature dependence. Okay, and so that experimental data, which is what went into those early sort of climate weathering models, like Walker and like Blagg, because that's where they had it from. And so then the question is, you got in the field and you measure stream chemistry, and you say, well, this should actually give us the real story because we know soils are a horrendous mess. And so what actually happens? And then you find that as I showed some of the data from Reby and from Gallardet, and there are many others that I could show, you generally tend not to get such a strong temperature sensitivity. It's there, but it's relatively weak. Whereas those same mineral phases, in fact, a little bit faster weathering ones are present in volcanics. And, of course, you have volcanic glass, which alters very quickly. And you can do that in the laboratory. And then when you go out to the field and you look at what's coming out of rivers in volcanic catchments, it's much closer to that strong temperature sensitivity that you predict from the laboratory rates. And so that's why I said that. All right? The complications in the granitoids and the soils that they make and the types of minerals that they have present seem to... that idealized single crystal in the beaker of water doesn't actually predict very well what happens in the field, where it does a better job of predicting what happens in the case of volcanics.
I guess related to the aerial, subaerial, and the climate regulations, I'm getting the sense we agree we need a hydrologic cycle. We need something above the ocean.
Yeah.
Also, right? What
Yeah.
we call continents. Has anybody done the calculation for how much you can get away with? How much land area do you need?
Yeah, it's a good question. I think that would impact on your time scale. So let's say if you had less land area available, right?
That's the thought process.
Yeah, then that's going to slow down the adjustment time scale to a perturbation in climate, CO2, whatever. As long as that land surface can be resurfaced through some erosion process or tectonic process, that's fine. But if you were to, let's say, stop plate tectonics, okay, And you would expect after some time with all of the, and take the mantle dynamics out of the picture if you don't mind me saying so. So after some amount of time, relatively rapidly, right, you would reach kind of a low gradient surface. And then that low gradient surface would weather, and then the weathering rate would go way down, and then you could build up CO2 to quite high levels under that before you would somehow remove it by some other process, right? And so that's another way to do it. And so having an active tectonic surface is important. And one possible reason why Venus went off the rails is maybe the tectonic environment was different there, and that those rocks were not able to consume CO2 at the rate necessary to keep the runaway of greenhouse from happening. That may be baloney, but polonium is a good element, so it's okay. Yeah.
Well, but you had lips up there too, so turn off plate tectonics. Let mid-plate volcanism.
Okay.
Something above.
Yep. No, lips could potentially be important, and actually, I'm drawing a blank. The paleomagnetist at Lamont, timescale guy, proposed in a PNAS paper, because now he's an NAS member, so he could publish it, and Dennis Kent, thank you, proposed that part of the climate drawdown in the Cenozoic is when the Deccan Plateau passed through the wet tropics before it got in its present relatively arid setting. That's not something you can a priori say is wrong, right? It might be true or it might contribute in any case. So the position of lips through time matters, right? The Columbia River basalts are I think it's relatively small as lips go, and it's relatively dry out there, so they don't have that big an impact, right? The Columbia River is ignorable at the current stage. But if you were to put the, if the Karoo occurred in the wet tropics or something like that, if it was wet there, yeah, you'd expect a big pulse of weathering. And actually, Yves Gutierrez has done some modeling of this at Toulouse, and he's found strong effects, right, where you get an initial, climate warming because of CO2 increase, and then a climate cooling because of then the accelerated weathering. Yeah, just one of those kinds. Kind of like what Mark was talking about, but in a different way.
Also, going out of the snowball Earth is a similar experiment, right? As if you wouldn't have the weathering cycle.
Yeah, so one of the questions is just to summarize quickly, under relatively normalish kind of conditions, right? It's really pretty hard to change the pH of the ocean very much, right? And you can change it a little bit, but it's carbonate buffered. And, of course, we're changing the pH of the shallow ocean right now because of anthropogenic CO2. You've all heard about ocean acidification. But on a geologic timescale, that acidified water gets mixed down into the deep ocean. It gets neutralized. In the long run, it's all good. We might not be here, but the oceans will be fine, A lot of plankton. The corals will be toast, right? But corals are... go see them now while you still can. Not just from ocean acidification, but other results. But in the long run, it's not easy to change the pH of the ocean very much. And so then the question is, how does changing the climate or CO2 affect the rate of ocean crust alteration? And it might a little bit through ocean temperature. If bottom water temperature was significantly warmer, one could see an effect there potentially. But under really bizarro conditions like the putative snowball Earth, maybe that was played a role, right? And in fact, it's not easy. It's really not easy to get out of the snowball Earth. If you actually glaciate over the surface and you build up CO2, Dan Schrag will tell you it can all be done fine, but as far as I know, nobody's really done a very happy job of really physically modeling exactly how you get out of a full snowball set of conditions. Because it's hard, even when you build up CO2 to very high levels, it's not obvious that you can overcome the albedo effects, right? So this is an argument that has been going on for a while, but anyway. But under really strange conditions like that, it's still not clear what happens if you had, 25,000 ppm CO2. In other words, atmospheric CO2, where where CO2 was approaching what we currently have for the concentration of oxygen, what that would do in ocean crust weathering, right? Likely to have an effect, but it's kind of way outside our realm of experience. So anyway, hopefully you get kind of the gist here, right? And, if any of you want to throw away your lives in frustration, then come work with us on surface chemistry and weathering processes, But it's very interesting, even if it's not easy to come up with simple relationships that describe all of these things.
So do you have a comment on the next best tracer?
On the what? The next best tracer. No, I think you need all of them, right? You need the whole kitchen sink. That's why God put 90 elements in the periodic table for us to play with, and otherwise we'd be out of a job, right? And so I think one tracer isn't going to give you the answer, right? And because each one is telling you something different, but you really have to think through carefully. It's a combination. You can look at the paleoceanographic record and say, okay, lithium goes up, strontium goes up, osmium, well, all that. They all are telling you something about something, right? But then you have to actually go back to the weathering interface and see what actually happens that gets the lithium or strontium or polonium out of the rock into the water. That's really the key thing. And that's where I spent a lot of my time in recent years, is trying to understand, I'm interested in the tracers because we get these long records of them, right? And yet, if we don't understand what the tracer actually represents in terms of weathering processes, we're sort of left to, writing paleoceanography papers where we do this a lot, so I don't want to. I don't think that's the right way to proceed. I think you actually have to dig into the dirt a little bit and see what goes on there. And that's what the Critical Zone Initiative at NSF is about, partly, not just about this issue, but really understanding functionally and mechanistically, as best we can, what goes on at that sort of meter-ish scale. And still we have trouble going from the nanoscale to the meter scale, but we also have trouble going from the meter scale to the large scale as well.
Okay, thanks again.